weird. That looks better. So I can shift it around like this. Where do you want it? Like here. And with the autofocus, let's see. Now if I do the lock thing, it shouldn't be refocusing all the time. Yeah, I think that's fine, right? Thankfully. What's that?
The like label on that.
Yeah, I probably better over here.
Yeah.
This slide is especially dumb because there's like a lot of text. Can you see it from over there?
The test?
Yeah.
I think it was pretty good last time when we did the lights off. Yeah.
You like it like this better? Okay. Hey, can you please open that so that we get at least some light? It's like some sort of. Okay, let's get started. Shall we? So the usual reminder about homework 1, somebody already submitted it, the deadline is on Friday. And now it should be possible to submit it to Canvas. Somebody was asking that on Piazza, so I fixed that. I think the deadline is like by midnight, but you don't have to wait that long. I don't advise to wait that long. Okay, so the last time we talked about coordinate transformations, and that's actually pretty important. That's what your first project will be about. I'll probably hand it out on Friday again, where you should hopefully be done with your previous homework. It will be a little more complicated project. So coordinate transformations, I was trying to explain a little bit before what are the affine spaces and vector spaces. Maybe might be helpful. I was thinking if I just put it like in contrast like this. So let's take a look at affine and vector spaces. What are the similarities and what are the differences? The thing is that they can look the same on the first look. Because in both, so if I'm, for example, in R2, both in the affine space and vector space, I have an elements of R2. I have some x and y coordinates of something, right? The difference is that in a vector space, I call them vectors. Whereas in a affine space, I would call them points. So it's really just like slightly different ways of looking at the same thing. Like you know from programming, from computers, that if you have like 32 bits, you can look at it as like one int, or unsigned int, or a float, right? So and it's still the same thing. It just depends how you look at it. So with these spaces, it's exactly the same way. So I have like x and y. And I can either look at it as a vector or as a point. So in vector space, we had like a proper formal definition of vector space. I could also do a proper formulation of affine space, but I don't want to bore you with that. I think the vector space one was boring enough. So in vector space there is the origin, right? That's the zero. Maybe I sometimes can put like a little arrow. The zero vector, which is always an element of the vector space, right? In a affine space, there is no such thing as an origin. So basically, every point can be an origin, if you think about it that way. Or maybe a better way to look at it is in a affine space, there is like no special point. There is no origin, no zero. And if I want to like measure coordinates, that's what we are getting to, we can pick any point there, right? So in a sense that more corresponds to the real space around here. There's no like really special point, everything would revolve around, right? Like people in history thought maybe that special point is like the earth or the sun or something like that. There's no special point like that. So if I want to measure coordinates of these objects, so in vector space I have a basis, right? So those are just some vectors such that any vector I can express as their linear combination. In affine space, I will have a coordinate system to measure coordinates. Coordinate system. Or shortly, just frame. Coordinate frame or frame of reference. People call it different. In different fields, it's sometimes called differently. These things are used in robotics, computer graphics, computer vision, and probably like a different community calls it slightly differently. So the reason actually why we are differentiating between affine and vector spaces, that's what I talked about the last time, is that in vector space we can do transformations such as rotation, scale, shear, but not translation, right? So in affine space we can do all linear transformations. So those are linear transformations. So these are all linear transformations plus translation. The point really was that the origin in the vector space has to stay fixed by linear transformation, right? I was saying the last time, it's obvious if you look at it as a matrix, if I multiply the zero vector by a matrix, I have to get zero base. No way around it. The only way around it is to switch to an affine space, which, as I will show today, I can still model with a matrix, but I need to do a little trick called homogeneous coordinates. So that's where we are getting. So these are so linear transformations plus translation. They are collectively called affine transformations. So they would be like basically what are linear transformations to vector spaces? That's affine transformations to affine spaces. And all it really means is adding the translation. And affine transformation, so linear transformations, I said it like 10 times already, so you must be already bored by this. They are represented by a matrix, right? And affine transformations, they are also represented by a matrix, but a special one, special matrix. A homogeneous, sometimes that's called homogeneous or transformation matrix. In graphic, it's called homogeneous, I think. But the terminology is not super standard. Some people might think that the homogeneous matrix is something different. So, and the affine spaces, that the homogeneous matrix, how it works, that's what I will try to explain today. So maybe just let me give you like a little picture here. So if I have a vector space, I know I have the zero somewhere, right? So here is my zero. And I have some bases. The simplest one is like a standard basis. And if I have some point somewhere, I can measure the coordinates with respect to the standard basis, right? I can also take a different basis, not the standard one, but a different one. And I can still measure the coordinates of the point with respect to the other basis, right? So in this case, I would be projecting on these vectors. So here's my point P. I can express its coordinates with respect to any basis, really. So in the affine space, I have a coordinate system, which is basically a basis plus a point. So if I have the same, so if I have some point here in an affine space, so here is my vector space, here is my affine space, and I define a coordinate system, I can like pick origin, for example, here. Any point can be the origin, and I can give it the standard basis vectors, and I can find the coordinates of this point with respect to this basis, right? What I do, I take this, so let's say this is like basis A, so this is origin A, this would be XA and YA. So I take the vector, which I get by subtracting 2 points. I'll explain it better in a little bit, but now just trust me that if I subtract 2 points, I get a vector back. So this is the vector which I get back, and this vector I can then project just like in a vector space and get the coordinates, right? So those would be my coordinates. I don't like the focus there. I think we try. Yeah, it's much better. Come on. What's it doing? It's breaking out. Okay, lock. No. Okay. Hope it will hold it. So what else? So I can pick a different coordinate system. So let's pick one that has a different origin. That will make it more interesting. So like, and also different basis vectors. By the way, they would not necessarily even have to be orthogonal, but usually it's convenient to pick orthogonal vectors. So this could be like some origin B, and I would have two vectors xb and yb. And how would I measure the coordinates of point P with respect to this coordinate system B? The same way, right? I would take the vector, basically subtracting these 2 points. So the point P minus OB, so both P and OB are points in the affine space. If I subtract 2 points, I get a vector. And the rest is just standard vector space business, essentially. Now I have already dealt with the origin. So now this vector I project to the basis, and I get my coordinates. The point of the affine space being that as I can choose the origin, the coordinates will also change with respect to the choice of the origin. That's also how I can get translation here, right? Here the origin had to be put. Here the origin can be changed, so I can easily do translation. So matrices are very nice, right? Because composing transformations, and that's something you will have to do for your next project, like that's because this is like what's happening in robotics. I was showing previously the model of a robot, which is just rigid links connected together. And what you need to get the aggregate transformation is compose all the transformations together. And in vector space, it's easy because it's just matrix multiplication. Right? Matrix multiplication is simple. You should by now remember how it's computed. MATLAB can do it just like this, right? So the point is that we would like to do the same things in the affine space. So we would like to find these special matrices which can represent affine transformations, which means including a translation. It cannot be done directly, right? Because linear transformations cannot represent translation. So we need to invoke some special concept, the homogeneous coordinates. So let's look at it, how the construction works exactly. So the construction works by setting up a projective plane. It's a very cool concept. So this is for R2. So I'm trying to model the two-dimensional affine space. So the main trick is to go one dimension up, to add an extra dimension. So if this plane is the plane on my R2, which I want to model, that's my affine space with points living in it, I will go one dimension up. I will add another dimension. So this x and y are the original dimensions of my affine space, and I will add a third one, the z. Now for every point like this one in the affine space, I can now define an array that goes through the origin of this coordinate system here. So the plane of my original affine space corresponds to z equal 1, right? So I'm modeling a 2D space in 3D by saying that I just pick one plane in the 3D space, and that's the plane that corresponds to z equal 1, right? Z equal 1 is an equation of a plane, and this plane corresponds to my affine space. And every point I can identify uniquely with array. Right? Array is just a line that passes through the origin. And this, by the way, the R3 here is a standard normal vector space, right? So this is how I'm converting the affine space, which is just this plane, to a vector space, but one dimension more. That's the trick here. That's the homogeneous coordinates. So let's look at these rays. The rays are cool. That's why it's called projective geometry. So if I have an array defined like this, so it goes through origin. So for alpha is the parameter of the array, and there are some other parameters x, y, and z. Then it's sort of trivial to figure out that the plane z equal 1. If z has to be 1, then alpha has to be 1 divided by z. So the array will intersect the plane at this point. X divided by z, y divided by z, and 1. Right? Or the x, y, z are basically, x, y, z is this, would be the coordinates of the 3D vector in the 3D vector space. So there is 2D affine space is being converted to 3D or represented in 3D vector space. So this vector x, y, z was a standard vector in the 3D space, so starting at 0 at the origin. And the vector represents the direction of my array. If I march along the array, that corresponds to increasing alpha, right? So if I start alpha 0, I'm at the origin. And if I'm increasing the alpha, I'm going across this array. If I had negative alpha, I'd be going the other direction along that array, right? And if my alpha is 1 over z, I will exactly hit this plane, right? And when alpha is 1 over z, and I substitute here, I get that this is this point. X divided by z, y divided by z, and 1. So that's the point corresponding to this vector. There's one exception that you can read here. The exception is if I have a vector which has the z coordinate 0. Right, so that would be a vector like this one, or like the x or y, or any linear combination of x and y. So that's a vector in the xy plane. This vector is parallel to the plane, right? So the line, the ray never intersects the line, right? The moment it's not parallel by a little bit, it has to intersect somewhere. But when it's exactly parallel, it will never intersect the plane z equal 1. And we will actually say that these rays, the corresponding to vectors x, y, and z 0, that they represent points at infinity, if you think about it. So it sort of makes sense, right? Because if I was going with this point further and further away, my vector would be like approaching more and more a vector in the xy plane. And you can imagine by like at the limit, if I finally reach the infinity, the vector would be completely flat. But more important, well, both are important, but this form is what is good to remember. Basically, when I took the affine point x and y, then I can represent it by the 3D vector x, y, and 1. Because that's the direction of the ray corresponding to the point. So either I can like think about it like represent the points with the rays or with their direction vector, or just with x, y, and 1. So maybe I'll actually elaborate on this, because I think the intuition that those are points at infinity, that's somewhat interesting. But what is more practical, I think, is that you can look at it this way. Here I will also explain why point minus point is a vector. So x, y, and 1. So these guys represent points, my 2D affine points, right? (2D affine space). And you can say that these, the x, y, and 0, that they represent vectors. So essentially, in the homogeneous coordinates, this is by adding this last coordinate, you obtain something where you can represent both points and vectors. And the last coordinate is how you distinguish between them. It doesn't matter so much if there is 1 or like 5 or like 0.3. The only thing that matters if if it's non-zero, right? If it's 0, then it corresponds to a vector, like a direction. The point at infinity, you can sort of look at it as a direction going somewhere, because you will never really get to infinity, right? But you can sort of interpret it as a direction aiming somewhere, if you recall the picture of the projective plane. And if from this, if all you remember is this, from this you immediately get these, how do I combine points and vectors? So obviously, if I take a vector and add it to another vector, so if I take some x1, y1, 0, and add it to some x2, y2, 0, then what I get is obviously x1 plus x2, y1 plus y2, and 0, right? So that's also a vector. So vector and vector gives me vector. That's what vectors should do, right? So that's nothing special here. What is more interesting is that I can add a vector to a point, right? Because what happens if I take a vector, so that's the same thing, this is a vector. If I take a point, it has 1 there, right? So if I add it, I get this, and 1. So this is a point, because it has 1 there. So adding vector to a point, of course, doesn't matter if it's commutative, right? I can add it either way around. I can do point plus vector or vector plus point, doesn't matter. And vector and point, either way, gives me back a point. From this, you can also see immediately that point minus point is a vector, right? Because there, well, I can do it just to have it all there. So this is 1 point. This would be another point. And of course, if I subtract it, I get some values here. It doesn't really matter. What matters is what is here, the last thing. And here it's 0, right? So this is what I was saying when I measure coordinates with respect to some coordinate systems. I subtract 2 points and I get back a vector. Yep. Now, slightly trick question. How about point plus point? Some of you might have seen this in some if you had some graphics courses or something like that. Slightly trick question. How about point and point? You know why is it tricky, right? Because if I just do the same thing I was doing so far, I will just do it, and I'll get there 2, which is, oops, it should be. And this is weird, right? What that should be? Anybody knows the answer by any chance? So the trick here is that in general, yeah.
Is that like a line segment?
There's a line segment, right? So what does that mean? I mean, sort of. Maybe it helps to look at it graphically, right? So if I add a vector to a vector, so I just do this thing, right? So, and this is my sum of vectors. That's what I was showing, I think, on the first lecture or something like that, right? If I'm dealing with points, I have a point somewhere, and I add a vector. Obviously, I get a point back, right? The same thing if I have 2 points, I can measure, like, if you think about it, points and arrows, that basically contains all this intuition here. But point and a point, how should I add them together? In general, this is not defined, so there are 2 cases. In general, undefined. It is, however, defined in one special case, and so if I take some scalars alpha and beta, and I take 2 points, x1, y1, and 1, and x2, y2, and 1. So this would be a well-defined point if alpha and beta sum to 1, right? For example, if alpha is 1/2 and beta is also 1/2, or alpha is 0.3 and beta is 0.7. Because in this case, the last coordinates sum to alpha plus beta, which is 1. in which case I get back a valid point. And what that geometrically corresponds to, I think that's what you were meaning by the line. If I like imagine a line here, so if I have alpha equal beta equal 1/2, and I take combination of these 2 points, P1 and P2, with 1/2, I get exactly this point, right? So this point is alpha P1 plus beta P2, or 1/2 of P1 plus 1/2 of P2. This was just to say this is not related. Okay, so this is what happens if I do point plus point. Okay. All right, so let's look how. Oh, there is actually one more note. That this the projective plane is also a useful model when you will be dealing with cameras, because this is exactly how the pinhole camera model works. I think we will get to it in a little bit, but the model is the same, right? You have some rays which are intersecting some plane. The plane you can imagine is the image plane, and the rays are like rays of light, and this would be like the focal point of the camera. So all the rays go through it, and this is basically how projection works. We will get to projection. Projection is probably the most complicated transformation, so we'll get to that last. Let's first deal with the simple transformations, such as translation. So the whole point of this business was to be able to represent translation or general affine transformation using a matrix. Right. So let's look how now we have this trick. Now we have the trick. So the trick essentially just consists in appending an extra coordinate of 1 for a point. And if I appended 0, it would correspond to a vector. So now we will be dealing with points, so there will be 1s. And how do I write a matrix that models translation? It's actually relatively simple, right? So if I have one point somewhere, like draw I can put the point here. So here would be my point P. So PA would be the homogeneous coordinates with respect to this frame. So I would take this vector. So let's say it would be like 0.5, 0.5. So my PA would be 0.5, 0.5, and 1, because we are in homogeneous coordinates, right? In general, some XA, YA. Now what I would like to is to convert the homogeneous coordinates to coordinates with respect to frame B, which differs from the frame A by translation of vector T. So if I do the same thing, this would be my, so this is my PA vector, and this is my PB vector. So it's fairly obvious that the PB thing is nothing but the Tx, Ty, 0 plus PA, right? Because all I need to do to convert there is add the original vector PA with the translation T, right? And the T vector consists of coordinates Tx and Ty when I'm looking at it as a vector. Again, if I go to homogeneous coordinates, and if it's a vector, I have to give it the last coordinate of 0 so that everything works together. Right. So, like for example, if this T, this looks like it's something, looks like it's like 2 and 1. So my PB coordinates homogeneous would be 2.5, 1.5, and 1. This is just the homogeneous one, last one. Right. So this seems to work, right? Everybody agrees? But what I'm trying to do is I'm taking the coordinates of point P with respect to coordinate frame A, and I'm trying to figure out what are the coordinates of the same point with respect to a different coordinate system B. Right? So this coordinate system A has some origin OA, and the coordinate system B has some origin OB. And what I have just shown that it's easy to explain it just by translation, just by summing, just by adding this vector translation vector t, right? The whole point of homogeneous coordinates is that instead of adding the translation t, instead of doing this plus operation, I can write the exact same thing using matrix multiplication. That's really the main point of homogeneous coordinates. And the matrix that does it, this magical matrix, is exactly this one. So it looks like identity, except for in the last column there is the tx and ty. So let's look what happens if I take my PA, so that's xa, xya, and 1, and I multiply by this matrix. So here I get xa plus, so you remember how matrix vector multiplication works, right? I'm doing dot product of this row with this vector, the second and the third. So the first one gives me xa plus nothing, right? So 0 times ya, so it's nothing, plus tx. So this is xa plus tx. That's exactly what I wanted here, right? So maybe if I write the whole thing, this is tx plus xa, this is ty plus ya, and this is 1. The second row multiplies xa by 0, so it's nothing. There is ya and plus ty, so that's this. And the last row, x and y, they both multiply by 0, and the rest, the 1 by 1 is just 1. So this is exactly the same thing as adding the vector tx, ty, 0. So in other words, this is the matrix that performs transformation of coordinates between two frames that differ just by translation. Yeah?
So in three-dimensional space, are we rotating the vector?
Yeah, that's a very good point. It is not a rotation, right? If it was a rotation, it would have to be orthonormal matrix. It's something more like some sort of shear. So in the 3D space, it's some sort of weird transformation. If you think about it, right, it's like one ray that gets like sheared to like another ray.
Okay.
It's not super intuitive. What is it in the 3D thing? You could probably figure it out if you were thinking about it long enough. Yeah. But yeah, so far I'm working just for 2D affine space, right? Like lifting it to this 3D space. In a little bit, I will explain how it works for 3D points. It's essentially the same thing. But okay, let me just repeat what was the point of this slide. The point was to derive this matrix GBA, which is the matrix of coordinate transformation from coordinate frame A to coordinate frame B, when these two frames differ only by translation T. Right? So, remember this similar things you will have to do in your project, which will consist in composing transformations for some kinematic chain. So for translation, or this could be like a general coordinate transformation matrix, and for the special case of translation, this is the form of that matrix. Yep, is that clear? If you already know some like graphics and OpenGL, that this is what's happening there all the time. So it would be sort of weird if we could do only translation and couldn't do the other operation. So obviously, in the same framework, with this homogeneous coordinates, we can also do rotation, right? We were able to do rotations before, just in a linear space, but we need to be able to do them also in the homogeneous space, because then the whole point is that we can just multiply all these matrices nicely together, and we don't really have to worry about like all the individual transformations. They just get nicely collapsed into one matrix. So the rotation, when represented by a matrix, by a homogeneous 3x3 matrix, you can just multiply it with the translation. I get a matrix of rigid body transformation. So let me explain how we do the rotation. It's simple, right? You could probably figure it out by now. So again, the point is to transform coordinates of one point, which is represented in coordinates with respect to one frame, and we want to get the coordinates with respect to a different frame. And then this time, the two frames or coordinate systems, they differ by rotation. So it's in 2D, so the rotation is always about the axis pointing up, and angle theta, that's our rotation. And the setup is the same, so the coordinates of the point, you can imagine the point is anywhere here, or it works for every point equally well. It's just an example. So the coordinates are again xi, yi, and the homogeneous one, and I want to get the coordinates. So the PA are coordinates with respect to one frame. Can try to draw it again. So here it's a little more confusing because the origin is the same, right? Here I'm basically not using the power of the affine space to translate the origin. So this would be my XA. Here would be my YA. And what I need to do is convert the coordinates into coordinates with respect to B. So into this XB and YB. It didn't fit super with the YB, like is the orthogonal projection of P on this axis. So the rotation matrix, that's what we talked about last time. So it has the form. So in 2D it's the cosine theta sine. So I'll just write it here. Cosine theta sine theta minus sine theta and cosine theta. So that's how a 2D rotation matrix works, right? And if I want to augment it to the homogeneous matrix, all I have to do is basically pad it with 0, 0, 1, 0, 0, 1. And that's because when I do the matrix vector multiplication, if I multiply it with this vector, then I get exactly the rotation of the part XA and YA, and here this thing does nothing, it just lets the one through, right? So if I carry out the multiplication, the XB and YB will be exactly rotated, XA and YA. That's what I wanted, because here the coordinates, they differ just by rotation. All I need to do here is to rotate the vector. And the homogeneous one is unchanged, right? Because the zeros here hit the X and Y, so I get 1 here. So here the coordinate transformation matrix G has this form. So in the homogeneous coordinates, we already know how to represent both translation and rotation. One thing that might be slightly confusing is that, so here I'm explaining from the point of view of changing coordinates, right? You could also be thinking about it as the matrices like acting on points, like translating the point somewhere and rotating them. In which case, the math is still the same, but the interpretation is different. So I'm just basically warning you, you have to like build a consistent mental image of what is going on here. So here the point of view is that I'm switching between coordinate systems. But equally valid point of view is that I am basically applying a transformation to points. So scaling is also very simple. So this is a non-uniform scaling scale of alpha in the x-axis and beta in the y-axis. So this would correspond to non-rigid transformation, saying that most of the transformations you'll be dealing with are rigid, but in some special cases you might need non-rigid transformations. So here is an example of a non-rigid transformation. There's another example, which would be shear. Some example of shear would be like this. So I just write the linear apart. Obviously, if I want it in homogeneous coordinates, I would just expand it, right? Do you know what the shear transformation does? So if I take something like, I take like image like this and apply the shear. What does it look like? Yeah, like basically slants, it will end up something like this. And this non-uniform scaling, that just means basically squishing in every axis, right? In x-axis, this is either squish or stretch, Depending if alpha is less than 1, then it's squished, it's making shorter. If alpha is bigger than 1, it's making longer, and the same for beta is the other axis. Scaling sometimes might be useful. Most important are really the rigid body transformations, because if you have like a robot composed of rigid links, those are rigid bodies. So the whole reason why are we doing this is so that we can nicely compose transformations. I was just trying to motivate this by the fact that once we have represented this as matrices, we know that composition of transformations corresponds to matrix multiplication. That's also true about the homogeneous matrices. So if I have a sequence of coordinate transformations, sequence of coordinate frames, that's exactly the situation we have in robotics, and the same situation you will be doing in your first project. We need to essentially find the individual transformations and then multiply them together. So here is like a methodology. How do you want to do it? I will show some examples in a little bit, but let's first go through this. So if you are dealing with a sequence of coordinate transformations, we like break it into the individual pieces. That's how you can make sense of it. So you can like do these 4 steps. So first, like draw a diagram just to see what's going on. I will show an example just in a second. And you can label the frames, so like frame A, B, C, or like frame for the wrist, elbow, shoulder. Then you need to find what are the transformations between these elementary frames. For example, between A and B, and then between B and C. Oh, I should have made the note that it's again very important if you are transforming from A to B, because that's not the same thing as if you are as transforming from B to A, right? That would be the inverse transformation. I mean, we haven't had inverse transformation yet, but just remember that if I denote it, the notation, you better have it consistent, otherwise it will be a mess. So here, the usual convention is that GBA means that I take coordinates with respect to frame A, and I turn them into coordinates with respect to frame B. So basically, like converts, you could also do it like even better would be like this notation. It converts coordinates with respect to A to coordinates with respect to B. So if I have some like point in A, I will get back point in B, right? And then I can keep going. Then I can take point from B coordinates to some C coordinates and so on, right? And because we know that matrix multiplication and composition of transformations is associative, I can just multiply all the matrices together. So if I have a chain of transformations, a first transformation from A to B, then from B to C, and then from C to D, all I need to do is multiply these 3 matrices in the correct order, and I get the aggregate transformation. That's why we'll do this project in MATLAB, because then there it's very easy to multiply the transformations. You will see the multiplied, the result. Just again, still just a 3x3 matrix, right? But that's all it is. No matter how complex chain of transformations you compose, you still get back a standard matrix. Okay, so let's look at an example. Here is a very simple one. So let's see what's going on here. So we have 3 frames here, 3 coordinate systems, A, B, and C. Some point there which originally starts in coordinates with respect to A, so that's where we can measure it. For example, that could be our camera or something. That's where we measure the coordinates originally in the frame A. Then there is another frame, so like this could be like some rotational camera on some translatable stick or something like that, if you want to give it some physical interpretation. Then I want to transform the coordinates into frame B, and the B is just rotated from A, so there will be a rotation. And then from frame B, I want to get finally the coordinates in coordinate system C. and the B and C, the transformation between B and C is a translation. So if the transformation between A and B is a rotation, we know how the matrix looks like, right? We just need to know the rotation angle theta, and we can compute this matrix. The same thing for the transformation between B and C. So all we need to know is this vector, the t, which has two components, tx and ty. If I know them, I can define the matrix, right? You should, yeah?
If it's GCB, why is the t pointing in the opposite, pointing towards B, from C to B? Like, isn't that supposed to represent the translation from B to C instead of?
Yeah, that's the problem. That's what I was sort of trying to allude to. It's sort of confusing. If you are transforming the coordinates, it goes really this way. Except, yeah, if you were transforming, if you were looking at it as transformations, it would really be going the other way around. So, well, so this I can explain it here. So this goes back basically to translation, right? So here this was the same situation, except it was A and B as opposed to B and C, right? So here if I take a point P in coordinates with respect to A, it's this short arrow, right? And if I now want the coordinates with respect to B, I have to add the t to it, right? So that the t really is in the correct direction. But you are absolutely right that if I was looking at it as like translating the frame A to frame B, I would need to have the opposite direction. Yeah. So if I wanted to take like some object, or take this space here and map it onto this space, I would have to take minus t, right? That's what I was sort of trying to explain by when I was talking about like these two views, that you can either look at it as change of coordinate systems or applying the transformations to actually like move something somewhere, right? And these two viewpoints are sort of dual. They are like inverse of each other. And you can easily see it. I mean, probably the only way you can really understand it is to draw these diagrams by yourself and pick some example, like the t is like 2, 1 or something like this, and figure out what does the algebra correspond to, right? So if I want to map, like if I wanted to take the point here and move it onto the frame B, then I would have to do minus t, right? Same way for the rotation. Instead of angle theta, I would have to pick minus theta. This is always confusing. I was also, the first time I saw this, I was also confused. The most important thing is to be consistent when you are doing the derivations, because if you start mixing the viewpoints, that will be a mess because the things are inverse of each other. So you have to be consistent. So I recommend to think about it as it's done here, as in terms of change of coordinate systems. That's basically what these slides explain. How to compute the change of coordinates of the same point with respect to different coordinate frames. Now, but that's a very good question. This is often a source of confusion. Nevertheless, if you remember this, you get it right. And the good thing is that if you're like playing with it in MATLAB or something, you can always plot it, right? You can always verify if the coordinates, if the matrices are actually making sense, or if you made some mistakes somewhere. So this was one example. I can quickly show like a more complicated example. For the project, I think you will be doing maybe even slightly more complicated exam. I think that's probably the best way how you will actually learn it, by doing a project, by actually computing it for some examples. So that's exactly what the first project is going to be about. So that's how you'll remember how it's done. So here I have some more complex structures. So here I have some solid base, and there are like two. It's like a simple robot, some backhoe thing. So this would be like a stationary base, and there would be two moving links, which are attached by two revolute joints here. And I have a bunch of coordinate frames here. So usually you associate the coordinate frame with like the last link, and that's where you, like if you had like a camera or expressing some sort of tool space, you would be expressing it with respect to the frame A. There would be some point, you would have the coordinates measured with respect to frame A, and you would like to figure out in what coordinates with respect to the world or the base coordinate system it is, right? And the way to do it is by walking this chain of transformations. So first look at what is the transformation between A and B. So this is a rigid link, so that will be a constant translation, right? Now this thing is a rotational joint, so here's a parameter of theta, which can vary. I suppose this thing is like a robot, so it can move. So that would not be constant. This would be constant, but the theta would not be constant. So here would be some rotation. Here would be another constant thing to D. I guess the D you could also skip because you could go all the way to E, because this is just a rigid link. But you can take as many intermediate frames, doesn't really matter. There would be another rotation which would bring you to F, and finally there's just like a constant translation back to G. So if you think about it, you can write the matrices for every single one of them, right? You could do GBA, you could do GCB, GDC, and so on. With a little bit of thinking, you would like figure out, aha, this is translating 2 units in the x-axis, right? So plug it into the matrix. How does it have to look like? Aha, this is rotation by angle. This one is rotation by angle theta 1. So from this, you know, if you know the angle, you know how the transformation looks like. So ultimately, you would get some matrix which depends on parameters theta 1 and theta 2. And I have to end here, but we will get back to it on Friday, and you will get a project on this on Friday as well. All right?
Oh, yeah.